Bueno, quizás podemos empezar. Ya estamos transmitiendo en YouTube, si no me equivoco, sí. Bueno, les damos la bienvenida a todos y en particular a Roni, que nos va a dar la segunda lecture. Me gustó en YouTube porque me escuchaba a mí también. Y bueno, después de la exitosa charla del día de ayer, Ronnie hoy nos va a contar sobre el modelo estándar y en particular el sector neutrinos, así que los dejo con él. So thanks, Ronnie, again for this second part of your lecture series, and you're good to go.
Muchas gracias. Thanks again for having me. You can hear me and you can see me. Yeah, good. So yeah, it's again a great pleasure. I'm also enjoying listening to some of the other talks, even though they're in Spanish. I'm able to follow some of it. Probably because it's about physics. My own Spanish is somewhat rudimentary. I learned Spanish when I was a mochilero in South America in the year 2000. So I traveled in Patagonia, and I really, I need to go back. So, qué bueno. Charla 2 of Introduction to Particle Physics and Neutrino Physics. I also have the real mate here. Good. So, what did we do yesterday? We started with the question just to set the framework of what drives particle physicists to go to work every day, or to get out of bed if in the days of working from Zoom. And the question is, how does the universe work? What's going on around us? And we have we have an answer that we can be very proud of. It is the standard model of particle physics. And that's great. It explains everything almost. Gravity is not part of the standard model, if you like. So, okay, standard model plus gravity. There are a few other phenomena that are not fully explained by the standard model. The dark matter that's holding our galaxy together, it's just a trifle little thing, but we're figuring it out. Actually, it's not a little thing, it's a huge thing that we're extremely curious about. And one other thing that is beyond the standard model is the masses of the neutrinos. So we will today we will get a more complete picture of what I mean by that it is beyond the standard model. The language, again, that we're using to even discuss these questions is quantum field theory, which is, as I said, a bunch of oscillators. A bunch is, oh, my pen is not working. Oh, it is working. It's, okay, now, sorry, technical problems. Yes, a bunch is infinity of harmonic oscillators, but we should not, what we're learning over, what we learned in the past several decades is that we should not get scared of these infinities. They're part of the framework and there are ways to deal with them. And so the MO, the modus operandum is you guess what the fields are in the theory, what the degrees of freedom are, and you understand what symmetries are in the problem and how the fields transform under the symmetries. And then you combine the fields into invariants, terms that are invariant under the theory, that do not transform once I do a field transformation. And we got to one example in the case where the symmetry is an internal sort of field redefinition, a phase rotation of the field. And if this field redefinition is local, it's a gauge symmetry. So I don't rotate the field everywhere in space-time. I only rotate locally. We wrote down this interaction, and remember this d mu is a covariant derivative, so it also has the gauge field in it. This is the term this is the kinetic term that will be present in any field theory in which the field is a scalar. And this other, we also stumbled upon the very interesting fact that once we impose a symmetry like this that's local, we always need to introduce this new degree of freedom, which is a new force, essentially, in nature. Good, so that was yesterday, recapping. So what will we do today? So there are a few more comments. I promise you that we're obsessed about symmetries. There are a few more comments about symmetries and quantum field theory and effective field theories. I'll define this term, effective field theory, briefly as an aside before we get to the standard model, the 3-2-1 model. So the standard model is again, on the one hand, it's extremely elegant. On the other hand, it has many moving parts. So we'll see that. We'll look at the Lagrangian and talk a little bit, or actually quite a bit, about the notation we use to write it. And then we'll pick it apart and talk about various parts. We'll talk about fermions and the QED part of the standard model, the quantum electrodynamics. Then we'll very briefly talk about QCD, since it is not the topic of the school, but it's worth mentioning. And then we'll talk about the electroweak sector, SU2 cross U1, and electroweak symmetry breaking. That's what EWSB stands for. Mañana, we're going to talk about fermion masses and neutrino masses. Okay, so that's the plan. If there are any questions, again, if there are questions, feel free to ask on Zoom, YouTube, unmute yourself and ask. Do not be shy. I'm very happy to, if we make a little bit less progress today, or in a little bit less progress overall, that's absolutely fine. It's a much higher priority that what I'm telling you actually makes sense. So, and it's easy for me to slip into jargon, you know. So, yeah. Feel free to interrupt me at any time. Good. So, a few odds and ends about symmetries and why they're important. In physics in general, so this is true for problems in mechanics as well. Every time we have a continuous symmetry, we have a conservation law, and we know conservation laws are super useful in life, right? The conservation of energy, conservation of momentum. We use these concepts to solve our day-to-day problems in physics and engineering all the time. So this is actually a deep statement that goes back to Emmy Noether and the Noether theorem. It's important to just pay homage to these facts. So, for example, the symmetry of rotations is tied to the conservation of, feel free to chime in the chat. If this symmetry is is rotation, then yes, angular momentum. Gracias. For translations, the symmetry is yes, of course, momentum or linear momentum. Time translations, of course, is energy. And so how about the internal symmetry? Yes, the symmetry of rephasing the field. That is less, that starts to come up only in quantum mechanics, whereas these first three are space-time symmetries, and they show up in our day-to-day life. So I'm in a swivel chair and I feel the conservation of angular momentum. Yes, charge. So charge is in the case that the symmetry is local, then there's an electric charge. If it's a global symmetry, we just particle number, which is equivalent. The number of particles is the overall charge divided by the charge of a single particle. So that's the same thing. Number of particles. And in the case of a generalized, the non-abelian symmetries, then yes, as Laura is saying, color, etc. The non-abelian charge. So color is the charge of QCD. In particular, of importance later in our lectures, probably we'll discuss it more tomorrow. There is the notion of lepton number, which is we'll define the standard model today, and the particles, which are the electron, muon, and the tau, and their neutrino cousins, are called leptons. And there is at least well, there may be a symmetry in nature that is lepton number, which is conserved, or at least approximately conserved. It may, in fact, be an accidental symmetry. So that will show up in this context. Good. So symmetries are important for conservation laws. And I just said the words accidental symmetry, and this is a very interesting concept. So what is an accidental symmetry? An accidental symmetry is a symmetry that is not a symmetry of the true short distance theory that I have. It is a theory that is emerging because I'm looking at, say, low energies, or inspecting the theory from large distances. So let's do a demonstration. So I'm even though I'm a theorist, I can do some rudimentary demonstrations, and actually this medium of Zoom and an iPad is very good for this demonstration. Let's discuss what is known in the world of physics as the spherical cow. So you may think, well, a cow is not spherical. So Roni, what are you talking about? But let me demonstrate. So I'm going to draw a cow. I need to be precise, so I'm going to change the thickness of my pen to narrow, and I need to be even more precise, so I'm zooming in here. Let's see, where shall I draw the cow? The cow is here. So here's the head of the cow, and it has a little body. It's a little cow, calf even. Oh, and this is your Argentina, so the culture of beef. Here's the cow. Oh, horns. Good. So here's the cow. See, it's not spherical. The tail is here. and the head is here, and the feet are here. And if I rotate it, and you can just rotate your head for me, because I cannot rotate the picture for you. Maybe I can. No, I can't. Yeah. So this is not a spherical cow. However, if we look at this cow at low energies, if we probe it with low energies, namely we look at it from larger distances, this is a pretty good approximation for a sphere, right? For a circle, because it's a two-dimensional cow. So this is an accidental symmetry, right? I drew something very small, right, deliberately, with the narrow pen, and then I zoomed out, and from afar, everything looks like a point, and a point is spherical. Okay, so again, not spherical, spherical, wonderful. I feel like an experimentalist. I'm actually doing something. Wonderful. So we can make this a little bit more precise, and there are concepts in physics that I'm sure you're familiar with, where this accidental symmetry comes out, and it's in Jackson's book of electrodynamics. And this is the idea of a multiple expansion, right? So if we look at the charge distribution, so here I drew some distribution of charge that has this perhaps this odd shape, and the distribution has a charge of delta R. So that's the delta R is an important scale in this problem. This is the scale at which I use to define physics. So that at the scale delta R, there's some more structure coming in. At larger scales, things are simpler. And that's the notion of that's how an accidental symmetry can come about. And so there's this hierarchy of scale where delta R is much smaller than R. So the cutoff in particle physics, we often call this the UV cutoff, even though we're well beyond the ultraviolet at this point, but this is a figure of speech. The cutoff is a much higher energy scale than the energy scale at which I'm doing my experiment. And let's say I want to write down the potential that I see with my eye here. Oh, I still have the narrow pen, which is not good. You won't see anything. The potential is just the overall charged. So in general, what I should do is I should write down the integral of Q, or actually rho, the charge density divided by R minus R prime, absolute value, and then I integrate over R prime, right? But then in chapter whatever of Jackson, we see that we can expand this. This is actually a derivative expansion, and the leading term is Q over R, and the next to leading order is, this is an R cubed. This is D dot R. D is the electric dipole moment of this distribution. And then there's a quadrupole term, octupole, et cetera, right? So we can capture everything in one order at a time. So let's talk about these terms. This term is of order the charge, right? And interestingly, this is spherical, right? This is It doesn't matter which direction I'm looking at. If my eye was over here, same distance away, this term would stay the same. But this term, because of this d dot r, is not spherical, right? This, I forgot to change back. Not spherical, okay? In fact, it has a shape like this. As I vary the angle. And this is of order delta r over r, right? This is the next order in delta r over r. And then, and so on. So this is order delta r over r squared. Okay, so there's a sense in which as I look from further and further away distances, the symmetry, the spherical symmetry becomes better and better because non-symmetric terms are suppressed. Good. So this is cool. This is the notion of an accidental symmetry. And this leads me to another notion that is extremely useful in quantum field theory and is in fact used to define the standard model to some degree, which is the truncation that we do in quantum field theory. And this is known as effective field theory, EFT. So we just did a truncation in the previous slide in the multiple expansion. And remember, in the first slide today, I reminded you what we said yesterday. The Lagrangian, or the Lagrangian density in field theory, this is a beast that has dimensions of energy density. So energy per distance cubed, inverse distance is energy in the units of h bar equals c equals 1. So this has dimensions of energy to the 4th power. So that's how particle physicists talk about dimension. Everything is in GeV at the end of the day. We have, so we know, for example, there's one term that's always there if this is a scalar field theory, which is this kinetic term. And then we add a bunch of terms, a bunch of invariant terms, and I think I even said all of the terms that are invariant. So how many are there? How many terms do you think we need to add? In principle, how many invariant terms will I be able to construct? At least one. Good. Depends on the group. That's also true. But let's say I have one. I can square it, right? So then what's the answer? So let's say if I have, I prepared some examples for myself. Let's say I'm allowed to write the term phi mod squared. I'm always allowed to write that. I'm allowed to square that. In fact, I'm allowed to raise this to the 13th power. This will now have dimensions of 26. So I would need to, in order to get the right dimensions, I would need to divide by the cutoff to the 22nd power. Okay, so that's an example of a term that I could write down. I can also take this kinetic term, which is also always there, and raise it to, I I don't know, the 10th power.
Sorry, Ronnie, we are not looking in the screen. What are you writing?
Oh, you do not see what I'm
No.
Oh, how, let's see, I'm scroll to the previous slide. Can you see that?
Yes, we see that.
Yes, yes.
Okay. Some people can see. So is this a problem in some sectors, or is this universal?
Oh
I
no,
think
sorry. Now I can see.
Bueno. Let's see. This is dimension 4. I raised it to the 10th power. This is 36. Okay, this is a very high order term. Okay, so from last time, every time I say that there's a bunch of things, and then I ask you how many is a bunch, it turns out that the answer is infinity, right? Because I can do this for whatever number. So in principle, this is true, right? So if I want to be really, really precise, I need to take everything into account. But this is actually, but for all practical purposes, this is not true. And we learned this in the previous slide, which is that the higher order terms were further suppressed. So I'll just state the result, but you already got a sense of it in the case of the multipole expansion, which is that higher order terms are they're analogous to high multiples. That is to say, and this is not trivial. But it's very important. Otherwise, we would need to keep track of an infinite number of terms every time we write down a field theory, and that would be disastrous. So at a given precision, we only care, we can just drop them. So we can say, okay, we will work up to dimension 4 terms. We'll only write the dimension 4 terms, and we'll drop everything that is of higher dimension. And that is indeed what we're going to do in the next slide. And the words, just to I'll say some words just so that you hear them, so that you're not surprised next time somebody says them. The terms that are up to dimension 4 are the renormalizable terms. There are reasons to call them that. So up to the renormalizable order, etc. And anything that is of dimension more than 4, we say that these are higher dimensional operators. So we'll talk tomorrow. We'll talk about the dimension 5 operator at great length. So this is and another term that is often used, that once you say I'm going to talk about the theory up to a certain order, what this means is that when I'm dropping terms like this beast, is that this is this is going to be a well-behaved theory. This will describe the physics pretty well. The fact that I dropped this very higher order term, so long as the energies in the problem, the distances that I will probe, will be much smaller than this cutoff scale, right? And so this is a good effective theory, and this is the notion of effective field theory. Okay, so this is these words are being said a lot because, for example, we know that the Standard Model is a good effective field theory up to, say, the scale probed by the LHC to a large degree, and maybe, and we have a lot of hints that it's good to a very high scale. Okay, I see some questions in the chat. Allowing d phi to the k for k more than 2 wouldn't require some kind of fine-tuning in order to avoid the non-boundness of the Hamiltonian. It may. Again, if that's a very good point, but this is related to what I just said. I think you typed your question before I said it, so long as the energies in the problem are much smaller than lambda, this term will be suppressed by a large power of this small ratio. So it's like saying, so for example, this a dipole term here. Sorry, I wanted to use the pointer. This dipole term will explode if I take r to 0, right? It'll be dominant over the monopole term, right? And why is that? Well, I've in doing so, in taking r to 0 in this term, I've extrapolated the theory beyond its validity. So yes, if I write down these terms to a certain order, and then I say, well, I take it to very large field values outside of the actual validity of the theory, I will have a problem like what you're pointing out, Juan. So this is very important to every time we write down a theory to know where it's to know your boundaries, know when it's valid. Thank you. This is a very good point. And are you generating accidental symmetries by dropping terms? Yes, absolutely. So in dropping this term, I generated accidentally, not on purpose. All I did was I said, I'm going to work to a certain precision. But as it so happens, once I drop the term that is of higher order, by accident, I generated this spherical symmetry. Now, in some cases, so as Laura is alluding, this can happen. It feels like this can happen quite a bit, and indeed, in the standard model, lepton number and baryon number, the number of conservation of protons and neutrons, say, these are accidental symmetries of the theory. There's one more case that we should since we're talking in this genre of questions, that this leads to, and what will happen tomorrow is that we will look at an expansion like this. It'll be for lepton number, and let's imagine for a second a case where I have this charge distribution, but the overall charge here sums to 0, right? And this is not crazy. The neutron is an example of this. The neutron is a collection of charged particles whose charge sum up to 0, right? So this term goes away for the neutron. And famously, the neutron has a dipole moment. It has a magnetic dipole moment. To the best of our knowledge, it does not have an electric dipole moment, which is one of the problems of particle physics, which is a completely different lecture. This is called the strong CP problem. But if we wanted to sort of describe the neutron order by order, we would write this down. Then we would say, the charge is 0, so we drop the first term. And then so at leading order, the answer is 0, which means, so if I have a precise experiment, I will have to take the next to leading order into account. This is precisely the situation with neutrino masses in the standard model. We write down all of the terms that are going to allow us to write neutrino masses in the standard model as up to dimension 4, and we'll find that the neutrino is massless at that order. So we will need to go to the next order. Good. Any more questions? Great, thank you. We're ready. Well, we're not really ready, but we're as ready as we would be in 3 lectures. So let's talk about the standard model of particle physics. So we said we need to define the fields and the symmetry. Let's do the symmetry first. The symmetry is 40 Poincaré. That's a fancy name for rotations, translations, and boosts. These are global symmetries, right? When I boost, I get into the car, the whole universe is boosted against me uniformly. There is a way of making these this is an aside beyond the standard model. There's a way of making these local transformations. So does anybody know what theory that leads to? If I make these symmetries local, what will happen? Okay, it's beyond the standard model, so write it in the chat if you know, and I'll come back to it. Quantum gravity, not quite. Not Susie either. Susie is a space-time symmetry, but quantum gravity is in the right direction. Just gravity, right? General relativity is the theory. It's a classical theory, right? It's not quantum. Famously, quantum gravity is something that we have not figured out yet. But in general relativity, I take these space-time symmetries and I make them local, and then space can be all gooey. And supersymmetry is a whole different story. Okay, so that's the global space-time symmetries of the problem. We'll restrict them to being global, and then there are SU3 cross SU2 cross U1. So again, SU is well, the S is special. It means I'm allowed to multiply by matrices that have determinant 1, and U means that they are unitary. So I'm allowed to make unitary rotations on a vector, a 3-dimensional vector in this particular case, right? So I will have objects that are 3-dimensional vectors, and the symmetry is that at every point in space-time, I'm allowed to do an SU3 rotation. And this is SU3 color. This will lead to QCD. There's SU2, and this is decorated by an L, or sometimes this is electroweak, or weak. So that's the same thing, only with a vector with 2 components. And then there's a U1, which is an overall rotation. So this little guy is called hypercharge. I don't know why it's called. There's nothing too hyper about it, but it does lead to QED and to charge later. So it is a charge. So these are the symmetries: 3, 2, 1, simple. Okay, the fields, there will be 3 copies. Why 3? I don't know, but there are 3. There are 3 copies of Qdley, Q, U, D, N, L, and E, fermions, and one scalar that was discovered almost to this day 9 years ago. At least the announcement was. So, and that's the Higgs field. Okay, so here I've listed. I knew that if I would write this down in real time, it would come out ugly, and this is like the standard model. I wanted it to look nice and neat. So here are the fields. So again, as advertised, so what's the notation? This number, let's pick on Q. This number is the representation under, oh, remind me later. The representation under the first group, right? So this is a triplet. So this is one of these objects that has three things. It is also, this particular field is also charged under SU2, and it is a doublet under SU2. So, and there are in principle higher order representations. This is the quote unquote fundamental representation of each of these groups. So QL is a bifundamental of SU3 and SU2. So I'm just saying words just so that you get used to them. U right, so this is the up-type quark, right-handed up-type. Oh, I didn't tell you, these little symbols, the left and the R is the left and the right. And we will get to that, we'll get to that at even great length tomorrow. But this talks about the chirality of the field. Is it a left and this is related to the helicity of the field? Is it, these are fermions, they have spin. Is the spin along or against the direction of motion of the particle? So are spin and momentum aligned? So basically, do you need to, in order to describe the motion, do I need to, and I'm now gesturing with my hands, do I need to use my left or my right hand to do it? Good, and so that these are these little, so some of these fields are left, some are right. This boldface 1 means that you are a singlet under this non-abelian group. So for example, U right does not transform under SU2 left. Okay. Whereas this left-handed lepton, and this is where the neutrino is living, it does not transform under SU3 color. So this is the construction. I'm now I have all of the building blocks. The only thing I need to tell you is up to what order am I going to keep terms? Because if I don't tell you that, we'll sit here and write terms ad infinitum. And the answer is that we will work up to dimension 4. Okay, so there will be a finite thing. What is the little, thank you, I forgot. This is the hypercharge. So this, the Q left has a hypercharge. So that's a charge under this group of minus a 6. Sorry, plus a 6. And by the way, I apologize in the name of all of the particle physicists around that there are several conventions of writing this. So in some places you will see U are defined as, and I'm going to pollute this, as a 3 bar, and maybe there's a little C here, and then there will be a minus sign. And that is a different convention of saying the same thing. The question is, which one do I want to call the particle and which one do I want to call the antiparticle, right? So a 3 bar is an anti-fundamental, which means that it transforms. So if the Q left under an SU3 color transformation will transform with a unitary transformation matrix times U left. But if I were to define a 3 bar, I would say that the 3 bar would go to a U dagger or a U inverse times the 3. But maybe I would, depending on my convention and notation, maybe I'd be multiplying on the left and not on the right and all that stuff. So there is it's a big enough theory such that different people have different notations, and we're going to see more of that in a second. Good. So so I told you what the symmetries are, what the fields are, to what order will we work. Let's write down a Lagrangian. So, and again, here notation is a big part of the story. Depending on the notation, the Lagrangian can either fit on a coffee mug, right, or on a T-shirt. My kids have a T-shirt. So if you're ever at CERN, the CERN gift shop has these cool cool things that have that have the standard model Lagrangian in a very condensed notation, right? It fits here. Or if you want to be super explicit about every term and every component of every field, and this is even not everything, I believe. Let's see. Yeah, for example, there were I said there are 3 copies of QUDLE, right? And I think this beautiful equation does not take, we would have to write parts of it 3 times in order to do it. So depending on the notation, you get varying results as to the size of the Lagrangian, right? So which one should we focus on? Which one should we study at depth? Well, one is a bit too simple. The one on the left is a bit too simple. The one on the right is impossible to work with. There are happy mediums. I found one as I was preparing for the talk. I mean, again, if I would have to choose, I would go for the coffee mug. Okay. Here's a reasonable medium option. So so this is again a big equation, but let's we can work with this. We can start identifying terms, and so the goal here is to for you guys to get to know this equation and at least know every interaction in the standard model, or when you see Pedro talk about charge current interactions and Kate will talk about neutral current interactions, you will know which line in this equation this comes from, right? So we're just going to spend some time dissecting this equation and getting to know it. So let's first of all let's give everything some names and identify what it is that they do. So the first line here, this is the this guy is the so remember in when you learned electrodynamics, you learned that E and the E field and the B field fit into this tensor, which is F mu nu, right? So that's what you should be thinking about. And now for the hypercharge, we can write this term. So the B mu nu is the F mu nu of hypercharge. This is the same thing for SU2, and this is this for SU3. So these are the gauge kinetic terms. Okay. So they're the fact that that electromagnetic fields can have non-trivial dynamics and electromagnetic waves, all of that stuff. These are so the fields that are, let's identify the fields. Oh, there's already new notation that it was introduced here. So in this slide, I had L sub L. This is the left-handed lepton, and this is a doublet, and the doublet is has two components, and I'm going to call one of them, the upper one will be called the neutrino, because it'll be the neutrino, and the bottom part will be the electron, or the muon, or the tau, depending on which generation. Whereas, and the neutrino will have the electron neutrino, the muon neutrino, and the tau neutrino. Okay, so these are these nu L and EL, and here they are, right? So this term involves the neutrinos, the left-handed neutrinos, and the left-handed electrons, and it has a derivative. So this is the kinetic term for leptons. And this does not look like the d mu phi that I talked about yesterday. This is because they're fermions, so the kinetic term for fermions looks differently. We'll talk about that a little bit. Here, again, we have leptons, and so this is the left-handed guy, and this is the right-handed guy, and there's this symbol called, so this is the mass term. And this is the mass term for the electron and its cousins. So this is the mass for the charged leptons. Okay. This term actually, strictly speaking, should not be here. So this is because I took this from a 2-page note that I found online by Cottingham and Greenwood. The note, so this equation and the all of the notation explanation of it fits in 2 pages, and it's attached to the end of these notes. So when I post this online, you can dive into this equation using this note. Notice that there's a field here, nu sub r, the right-handed neutrino. And when I define the standard model for you, there's no nu sub r. And that's because I don't know whether nu sub r exists. Okay, so what so I have no complaints to Cottingham and Greenwood for writing this equation in this wonderful notation. They just made the assumption that neutrinos, if there's a notification, ignore this, that neutrinos get their mass in a particular way. And we'll talk about that tomorrow. So these are neutrino masses. So I'm putting a star here, which means I don't actually need this line if I'm strictly speaking about the field content that I introduced for you. In the case where neutrinos are Dirac particles. If neutrinos are Majorana, this line would look different. So we will talk about this. To get to it, I may need to skip some other things, but this may be more important. Now, this line looks a bit like that line, and this is the kinetic term for quarks. So all of the fields that were charged under SU3. So as you see here, again, they chose to, so SU3 was kept implicit in this equation, but SU2, because it is about to be broken, it's more useful, it's more important to break out the different components of SU2, but SU3 remains unbroken, so we can just throw that into the notation and drop those indices. Very good. These are masses for up-type quarks. No, this is not up. This is down. So the down quark, the strange quark, the bottom quark. Apologies for the funny names. Masses. And these are masses for up quark, up-type quarks. Good. How am I doing with time? Okay, 1 hour. This is it. This is the, one last line. Very important. This is, finally, we see d mu phi, the bar is one of the symbols of charge of complex conjugation that we tend to use. So this should look familiar. So this is essentially everything to do with the Higgs field, the kinetic term and potential, the potential energy of the Higgs. So 10 years ago, we thought that this was there, and we've never seen the actual particle. 9 years ago, we knew it was, we knew it's there, and we measured this parameter for the value of it for the first time. Very nice. Questions? Any? So there's a lot of details here. Maybe I'm forgetting something, like defining something. So feel free to ask me. But this was sort of a bird's eye view of the standard model Lagrangian. And now we will sort of dive in a little bit and zoom in on some parts of it that deserve a little bit more detail. Okay, one sip of mate while you gather your thoughts. Okay. Okay, so before we, so fermions. Fermions can be a real, there's a reason why we always start teaching quantum field theories with scalars. And the professor that taught me quantum field theory taught us everything there was to know about scalars. And then in the last lecture, he said, oh, by the way, there are fermions, and then rammed it into our throats. Which is, I totally understand why he did that. Because fermions have this added baggage of having spin, and they carry angular momentum with them, and angular momentum needs to be conserved, and we need to make sure of that. Because of that, there are all these symbols that you see in textbooks. So, for example, this sigma and this sigma these are Pauli matrices. So this, by the way, is these folks chose two-component spinor notation. So this is what I'm alluding to. There's a bunch of notations. Often you will see gamma matrices. Let's see. So for example, on the coffee mug, John Ellis, who I believe wrote this equation, wrote d slash. D slash is the covariant derivative with this mu index contracted with a gamma matrix. And I'll define the gamma matrix in a little bit, but that's a 4x4 version of Pauli matrices. So all this baggage of sigma matrices and gamma matrices, this is all meant to do something that is actually quite simple. It's just that it's tedious to actually do in practice, which is to take care again of angular momentum and spin conservation. So so step back away from the standard model for a second. Let's just think about just the quantum mechanics of 2 spin-1/2 particles. If I have 2 spin-1/2 particles, remember the rules for adding angular momentum. With 2 spin-1/2s, I can have this state. This is often called the singlet, right? And what is the total spin of this state? feel free to write it out in the chat while I make sure that, so this is called the singlet. This has the total spin of 0, okay? And then there are these 3 states. So you see the spin along the z-axis is 0 for each of these, but when I put the minus sign between them, then S total is 0. There's this beast, or these 3 beasts. Now I'm going to put a plus sign between them. So because there are 3 of them, often this is called the triplet. And what is the total spin of this? Gracias. S equals 1. So in the language that we use to describe the transformation under rotations, this is a scalar. So this is an invariant term, right? It is invariant under rotations. It will not transform at all. So if these were fields, I would be able to write this term at the Lagrangian. This term I'm not allowed to write in the Lagrangian because it transforms under rotations in the sense that I can start with this and then with this state, and I do a 180-degree rotation, I'll end up with this state, right? So this I'm not allowed to write as is in the Lagrangian. So this thing is just to complete the, this is a vector, right? And so for example, and indeed we do write terms like this scalar in the Lagrangian, and these are the mass terms. So notice the mass terms here. Okay, it gets more complicated. The mass terms here, ignore this phi, involves just 2 fields. So this is a good candidate. This spin structure is a good candidate to write a mass term. Whereas this vector is a good candidate to write something that is a vector, which is a current, right? A current which is flowing in a particular direction. Another way to say this is that if I take this thing which is covariant and not invariant, and I contract it with a vector field, then I can get something invariant. That vector field is the photon, for example. So this coupling to the photon. So what is the moral of this slide? The moral is that all of the junk you see in standard model in particle physics Lagrangians, which is sigmas or gammas, and sometimes there's a gamma 5, which I'll mention in a second. All of that is just notation. To keep track of all this, right? All the Clebsch-Gordon coefficients that are associated with the addition of angular momentum. And because so in quantum mechanics classes, we spend whole problems just adding angular momentums and figure out the Clebsch-Gordon coefficients. In particle physics, we need to move on from that. We can't spend a lot of time. So people invented a lot of notation just to automate the process of this, and with very good reason. So I sound like if I'm whining, I don't mean to. This is just that it's very good that we can automate this. But just when you see sigmas and gammas, just know, okay, this is taking care of the conservation of angular momentum in spin for me. Good. So some of the popular invariants, so now we can start building invariants for real. Here, these were just toy invariants. What do invariants really look like? So for a theory with fermions, so a Dirac fermion has 4 degrees of freedom. There is the spin up and the spin down, each of which has a particle and an antiparticle. So that's why there are 4 degrees of freedom. In particle physics, since everything's moving very fast, we talk about spin up and spin down. In order to talk about that, you need to define the z-axis, right? The axis of measurement. In particle physics, where we define that as the direction of motion of the particle, in which case it's not up and down, it's left and right. So immediately the first thing that happens is we talk about a left-handed helicity and a right-handed helicity of particles. So there's a left-handed particles, right-handed particles. There are the particles and the antiparticles. And the invariants that you will often see, for example, I can take, so psi is the generic name for the 2-component wave, the 2-component field, which is also called a spinor. Bars are complex conjugation. And again, there's notation, and again, you can go to that note at the end of my notes, and more of the notation will be spelled out. I will not have time to define everything, but this is one invariant that's important in life. These sigmas are the Pauli matrices. Pauli matrices, there's sigma x, sigma y, sigma z, or sigma 1, 2, and 3. When we decorate them with a mu, there's also sigma 0, sigma t for time, and that's just a unit matrix. Okay, so this is a 4-vector of Pauli matrices, and what's more common, so in this equation, the size are 2-component spinors for left and for up and down, and it's convenient to put together a 4-component object, which is that. So this is a definition. So this is psi without the left to right decoration. And then there's a condensed, and this is maybe the most common notation in actual calculations. And then in order to do that, we need to invent a 4x4 matrix, which is the gamma, which has a sigmas on the diagonal, and one of them is tilde. There's a minus sign somewhere. Let's not get into that. So this thing is the vector. So if you see this, you should really think about this vector, right? That's a vector. and this is the thing that couples to photons, right? So let's see that we can see that on the coffee mug, right? Here it is. Psi bar d/psi, and the d/ is this gamma matrix times the covariant derivative. Okay, so this is the kinetic term for the fermion, and we found the vector. So the photon inside the covariant derivative couples to this current, which is this thing. Something that's important in, oh, I changed color because writing on the mug had to be in gray. Yes. So psi, I could have taken exactly the same term, and to save time, I'm just going to copy with a minus sign in between. In order to get that minus sign in the 4-component notation, I need to introduce another matrix in the middle here, sandwiched. And this is gamma 5. By the way, this is a particular, there are textbooks in which they choose a different basis and then the gamma matrices look different. So beware. So this is a matrix that introduces a minus sign for the right-handed fields, but not for the left-handed fields. So this is the pseudo vector. So it's like a vector, but it does not. There's an additional minus sign when we do a left to right transformation or a mirror transformation, parity. Magnetic fields are an example of a magnetic and electric fields behave differently under parity. In the mirror, electric fields get a minus sign, but the magnetic fields stay the same. So that's an example of pseudo vectors. And electroweak theory, the weak gauge bosons, the W's and Z's, the Z, for example, couples to a linear combination of a vector current and a pseudo vector current. So that's why this is important. Also, sometimes you will see definition of P left, which is 1 plus gamma 5. There's probably a half or something. I think this was in Pedro's notes. And this is a projection onto the left-handed. So that's sometimes you want to use 4-component notation, but I want something only to talk to left-handed fields. I introduced this 1 plus 1 or either plus or minus gamma 5s. And then finally, in the list of most popular invariants, which in 4-component notation is psi bar psi, this is the scalar. So that's what mass terms look like. I can just write down this term without coupling it to anything. Questions about all of this? I know that this is a bit much. Let's see, how am I doing with time? 15 minutes. Should I skip QED? Yeah, I think I have covered a lot of this. So this is just, so QED, the theory of electrons and photons, roughly speaking. Now I've written it. So this was in the Lagrangian, for example, here is the electron, the right-handed electron coupling to its covariant derivative. So I'm finding, and the same is happening here. So I'm pulling out these terms as well as this, but now it's the photon, which will be a linear combination of hypercharge and one of the W's. So this is this theory, or in the even more condensed notation, d slash plus me. There's one thing I need to mention here, which is I snuck fermions in. So yesterday I talked about harmonic oscillators and all that stuff. Fermions are also harmonic oscillators. They have some quirks that I will not go into, but the equation of motion that they adhere to is the Dirac equation. And so this Lagrangian, once I solve its Euler-Lagrange equation, will give me as an equation of motion is the Dirac equation. So the Dirac equation is the Schrödinger equation for relativistic fermions. Good. So that so this is the action. This is the Lagrangian that gives me that theory, and that lines up. One other nice feature of this theory is that remember d mu is the covariant derivative already has the photon coupling built in. So really, photon coupling is part of the kinetic term. Kinetic terms are the same for all fields. So this means the photon automatically couples universally. I'm sure I'm making spelling mistakes. So that's the photon couples to charge, and that's sort of built into the theory. This other term at the bottom, this is the kinetic term for the photon itself. This is nothing but so in the Lagrangian, this is E squared minus B squared in the language of E and B fields, right? F mu nu has its definition. Let's not write it down. So this is the thing that in Hamiltonian notation, it gets a plus, and that's the energy density in the electromagnetic field. So this is QED. So having seen the whole Standard Model, looking at QED is really it's a brush. It's like fresh air. You're like, oh, okay, that's simple. Good. QCD. Again, I think in the interest of time, since I see that I'm falling behind, I'm not going to say too much about it, except that it's in some ways it's very much like QED. The gluon, so there are mild differences. For example, there are 8 gluons. The 8 comes from 3 squared minus 1. So it's the number of traceless 3x3 unitary matrices. Unitary? Hermitian. So that's the gluons, but the notation is reminiscent, and this is also similar. So these quarks are triplets in color space, all right? And there are 6 of these quarks: up, down, charm, strange, bottom, top. The big differences from QED is that this is a strongly coupled theory. So this becomes strong at around lambda QCD, which is around 200 MeV. And this is why LHC collisions are so interesting, right? All these jets, because the theory is strongly coupled, more and more particles are produced, as even if you just produce one quark, fragments, all that great stuff. Again, because this is a summer school about neutrinos, there are people who do QCD for a living. Some of my best friends, but there are also people who do neutrino physics for a living, and this is what we're talking about this week. So moving on. Now we get to the Electroweak sector. The Electroweak sector is, remember, this is SU2 left. This was U1 hypercharge. This symmetry will get broken to U1 QED. So first of all, let's count gauge bosons. The SU2 group has 3 generators, which are essentially the 3 Pauli matrices. And U1 has 1 generator, that's just a phase, so 3 plus 1. And this will go to just 1 leftover unbroken gauge group, which is the photon that you're using to look at me. So let's talk about the 3 plus 1 are going to be the W. So there's a W0, 1, 2, and 3. Oh, sorry. What am I doing? W1, 2, and 3. And then there's the hypercharge. In this combination, with some linear combinations will get a mass, and one linear combination will not get a mass. So the ones that get a mass are the W plus, the W minus, and the plus and minus refer not only to the fact that you take W1 plus or minus IW2, but it's also the actual electric charge of the particle. There's the W0, also known as the Z. So let's give it the name that we usually use. So that will be some linear combination of the 3 and the B. And there will be plus the photon. So these guys are charged. And these two are neutral. But the W's and the Z get a mass and the photon does not. Okay, so that's what's going to happen. How does this happen? So in the remaining 5 minutes, we'll talk about the heuristics of how this is happening, how the symmetry is broken. And I'm sure you've seen this picture of the Mexican hat potential, but we'll go through it very quickly. And I think we will have to decorate this with equations tomorrow. And then I'll have to make some tough decisions about what I'm dropping out, because I see I'm moving slowly. So the Higgs potential, remember, the Higgs got a potential which was here in our bird's eye view of the Standard Model. And so, and I'm deliberately already writing it in a way that it's clear that the minimum of this potential is going to be when phi squared is v squared, and not when phi is v, is not when phi is 0. So this is the point. This is phi equals 0, which is the point that if I do a rotation on this Mexican hat around its axis, this is the point that that does not move is invariant. The minimum of the potential is covariant, right? It shifts, right? If I do a rotation, it will move sort of this way. So I have the potential itself overall is symmetric, right? But the vacuum is not symmetric. Now there's a problem with this picture, which is that the symmetry of rotations, and I apologize, I'd ask you what the problem is, but we have like 3 minutes. The symmetry is completely broken. There's no more symmetry. I can't rotate this around any other axis. This point, I mean, the vacuum. Once I draw a dot on this hat, I can, at that point, I cannot rotate this and keep the picture the same at all. So though this is a very useful picture for electroweak symmetry breaking, it doesn't capture everything because remember here I had SU2 cross U1 broken down to an unbroken symmetry. There is a symmetry that's left over. So here's a better picture. So now I'm not drawing the potential, I'm just drawing the field space. And why is this a good picture of SU2 space? So here I'm SU2. Remember the generators of SU2 are these 3 Pauli matrices. That's like a vector. And indeed, I think SU2 turns out to be isomorphic to SO3, which is rotations in, these are orthogonal rotations, which are just physical rotations in some space, some 3-dimensional space. So that's why this sphere is symmetric under SO3, right? If I take the center of the sphere, and forgive me, this point is meant to be at the center of the sphere. So, and this is, by the way, if you're doing anything with quantum information science and qubits, this is the Bloch sphere, okay? The center is SU2 invariant, right? So let's imagine there's a potential that I draw on top of this in yet another dimension, such that the minimum of the potential is on the surface of this sphere. So so imagine, if you will, a Mexican hat potential, but a 3-dimensional one. So the surface is symmetric. So I can rotate the sphere and it's still a sphere. And that is the minimum surface of the potential. But now you're going to force me to pick one of these minima. So I'm going to pick some place. In homage to, I'll pick it on the southern hemisphere. Good. And so now I picked this, and now notice there is a symmetry left over. So once I pick a point on the globe, there is still the symmetry. So if the point is where I am, the symmetry of me rotating on my chair. So this means that SU2 in this particular case is broken down to a U1. And that is what's going on in field space in the standard model. Well, actually, that's not all what's going on, because there's another U1 in the story. This field transforms. Remember the phi field is a 1 for QCD. It was a 2 for the SU2, and it had a +0.5, I believe. correct me if I got the sign wrong. So it's also charged under U1. So what's happening is that the phi field, by being a 2, it breaks SU2, and it down to a U1. It breaks the U1 hypercharge, but there's a linear combination of the U1, the unbroken U1 and hypercharge that is left unbroken. So that's essentially heuristically what's going on. What this does sort of to the mathematics of mathematically in the field theory, we'll talk about tomorrow. We will probably have to skip some of it because I want to get to show you, for example, how neutrinos interact. So I'll make some tough choices, but I'm happy to stop and take any more questions and give you guys a break to go and refill your mate.
Thanks a lot, Ronnie, for this talk. Si alguien tiene alguna pregunta, por ahí podemos aprovechar estos minutos. No, so you gave them a lot to think about.
Yes, there is a lot. There is a lot. I'm also despite my incompetence, I didn't manage to join the Slack channel. So I will post these slides onto the Slack channel, and it'll also have some of the material that I didn't get to. And if you have any more questions, feel free to shoot me a message on Slack.
Fantastic. Thanks a lot. Muy bien, bueno, les recuerdo entonces que la próxima charla de Elena va a ser a las 12, así que, bueno, pueden, como dijo Ronnie, pueden tomar mate de acá hasta las 12. Entonces, muy bien, cortamos la transmisión.